know if we can see your screen, but she said she cannot unmute.
All right. Can you hear me?
Yeah.
Wonderful. Oh, I never used this feature. I could not unmute myself. Thank you, organizers, for having me. I wish I were there with you all. Hopefully this pandemic and weird world situations will be over soon. But I'm excited to chat with you on the topic of bridging the gap, the representation gap between humans and machines, especially focusing on unique challenges in vision. Before I jump into the talk, I'm curious, how many people are in person? I know there's quite a bit of people on remote, 72 people I'm seeing.
I went around to take a picture, so I got away from the laptop. Actually, there is a lot of people in person. I'm really bad at counting, but I would say roughly equal as there is on Zoom.
Nice. Wow, that's awesome. Yeah, I wish I were there. All right, well, I'm going to pretend that I can see you and project you.
People are telling me there is more, so goes to prove my point that I'm not good at counting people visually.
It's awesome. I'm going to imagine you all in my head, thinking about my previous sessions at previous CVPRs. So without further ado, let's jump in. Okay, so this audience doesn't need to be preached on the importance of being able to talk to machine learning models, where the goal is to do usuals. We would like to understand how machine learning models work, to know what they're doing, to use AI more responsibly and more effectively, et cetera, et cetera. So I'm going to skip all that and to jump right into what this problem technically means to me, with the goal to clarify the core technical challenges, especially in vision. So one way to view interpretability is to view it as a mapping between representational space of humans and machines. So let me explain what I mean using this simple diagram. The circle on the left represents what humans know, things in humans' representational space. Any member in this set is something that makes sense to us, like the cat is big, is in part of this circle. The circle on the right represents what machines know. There's probably some overlap between the two, but it's likely that there are things we don't yet have a representation for. If you enjoyed watching the match between World Go champion Isidore in 2016 versus AlphaGo from DeepMind, you might remember this move 37 that puzzled every Go player at first, but then this move turned out to be like the one move that made AlphaZero to win this game for this particular match. And to this day, many Go players are currently talking about this move, trying to understand it. So it's probably fair to say that we don't yet have a clear way of understanding this move 37 using our representation. So that lives in this part of the circle that only machines know yet. So zooming out a little bit, in high level, the ultimate goal of interpretability is to develop this language between humans and machines so that we can talk. And this language comes from having a common representational space. In other words, humans and machines have a common vocabularies to talk to each other, and those vocabularies lie in the intersection of these two circles. And the language will shape our working relationship with AI. As elegantly described in the book by Brian Christian, The Alignment Problem, the ultimate goal is to align our values to what AI does and how it does it. So how do we bridge this gap and develop this language? We do it by first expanding what we know through dialogues and collaborations with machines, and learning more about machines will enable us to build machines that can better align with our goal, as we've seen in many of those spotlight presentations just before this talk. And doing so will increase the overlap between what we know and what machines know. So let me operationalize what I just said in more technical terms. Suppose we can conceptualize a concept in humans' representational space as vector CH. Perhaps this vector means striped concept or striped patterns. So we never really observe this vector, but we know it exists, because if not, humans would not be able to communicate with each other. We have a common vocabulary and we share some representational space. And we have some finite samples of what striped means to humans. Now, assume that this concept is something that both humans and machines know and know how to represent. So stripes lives in this intersection of two circles. In other words, there exists a CH as a vector in the machine's representational space. And our goal is to estimate CH hat in machine's representational space. Signals from this CH will be naturally noisy because we never have all the exhaustive examples of stripes. There will be other information that comes together, typically with striped concepts like t-shirt concept that highly correlates with it. So one way to learn this CH hat is using this work called TCAF from a few years ago. I'm not going to talk about this work in this talk, but it's a simple method to use the CH hat to talk to the machines. For example, you may wonder, okay, so what do you do with this CH hat vector? Once you can represent our concept in machine space, we can ask interesting questions or have a conversation. So for example, in this TCAF work, for example, we can say, was this striped pattern influence your prediction of zebras by perturbing this vector and see changes in machine's prediction? We're also interested in the other way around. So if there exists a machine concept CM, and we're interested in learning more about it. For example, there are many machine learning models that can do things better than humans. The AlphaGo from DeepMind is a good example. How does it play the game of Go? What if this model is solving a scientific problem that was previously unsolved? There has been huge interest in learning a new way to solve our existing problems. So let's again assume that this concept CM is something that we can comprehend. So this might require expanding what we know, but let's say it's something that we can learn eventually. So there exists this CM in our representational space. Then our goal is to estimate that CM hat and explain it in a way that we can understand. So in essence, developing this language is really about, given limited observation, estimating CH hat and CM hat. Because once we have the concepts in ways we can understand, we can start having that conversation. What's also important is to know when we simply cannot estimate it. So for example, if human concepts simply don't exist in machine space, we would like to know rather than mistakenly take noise as a signal. And that's something, perhaps an area that is less explored than other parts of this question. So as many of you know, that there has been much advances in solving this estimation problem in vision. And this talk is going to be about things unique to vision in bridging this gap, challenges and opportunities. So I'll share things that we need to keep in mind as we leverage this power of visual modality. So let's start with some challenges. One of the challenges in vision actually lies in us, not machines. Humans have amazing ability to connect the dots. There's even a word for it, apophenia. This means that our tendency to perceive meaningful connections between unrelated things. And this term has come to describe a human's propensity to unreasonably seek patterns in random information like gambling. So this phenomenon happens a lot in vision too, perhaps more severe, perhaps compounded with Gestalt effect, where human has tendency to group things together and assign meanings to them, or connecting unconnected lines to see full object when you're really only seeing parts of it. So when I say, oh, come on, that's you don't do it, do you? This is just some things that crazy people do. The time that I observed this phenomenon in real life was when I showed these two pictures to audience and asked them if they can tell which explanation is from a trained network and which is from untrained network. Many folks are really confident that they can see something in explanation from trained network that they cannot see in untrained network. The truth is, though, that I often switch these labels. So I put trained network with the label of untrained network. And people are really surprised when they learn that they were able to read something that doesn't exist. And this is a universal phenomenon in humans. And I'm willing to bet that none of us are safe from it. as we bridge this gap, it is really important to sanity check of our own conclusions and each other's conclusions. Do we really think that human concepts exist in machine space? Do we really think that we just discover a new machine concept? Being skeptical about our own selves is even more important in bridging the representational gaps. Here's another example that supports just how different the way we see the world and machines, just to iterate that there's no basis for feeling like we understand what we see. These are two set of pictures and explanations from two different models, model A and model B. And I don't think I can tell them apart. They look the same to me. But it turns out that neural network is able to see what we cannot see. So when we train a neural network to tell apart these two sets of explanations, it can tell which model is an explanation come from with very high accuracy, up to above 95%. Even when these two models are essentially identical in every other way, other than different seed, the data architecture, all the same. And the other way around is true too. Here are explanations from two different methods, gradient and integrated gradient, very familiar to this audience. I think the gradient visually looks different. Like there's some differences I can't describe in words, but I feel like I can tell than integrated gradient. But to machines, these two looks pretty similar. A model trained on one can easily generalize to the other. So this work highlights just how different machines and humans represent these black and white images. So we need to give a great care in our interpretation of these pictures, because there's just a lot we can't see and a lot that machines can't see. I'm going to fix my keyboard because it's doing beep beep on me. Let's see if that fixes it. Oh, by the way, if you have questions, please jump in anytime, either in person or virtual. And maybe organizers can tell me if there's a question. So you may ask, well, so why does it matter that our interpretation of this explanation? At the end of the day, the goal of explanation is to be useful for some end task. So are they useful? So in this work, our question was to see if explanations can help detect errors in machine learning system. Pretty common things like labeling errors or spurious correlation at training time, or maybe auto distribution or mismatch in pre-processing at test time. So to test this, we intentionally inject errors in the system of such kind. Then we showed an input image and a prediction and an explanation, many explanations are popular in the field, to different methods to each group. So some saw saliency maps and some didn't. Then we asked our subject if they would deploy the system. And we're testing whether explanations can help them validate the machine learning system. The results were a little bit disappointing. The only error the humans could detect this way was spurious correlation. So in a follow-up work, we ran another study to see just what kind of spurious correlation humans can detect in medical domain. Some spurious correlations might be visible, like this MGH tag in the left top corner that does not carry any diagnostic information, but it's there, it might be correlated to something else like Gaussian blow, which is not really visible. TLDR is that existing methods can help you only if you know what the spurious signals are ahead of time. So as a baseline, here's a normal model that is not using the spurious signals of MGH tag, and here spurious model that are using those tags. If you knew MGH tag might be a problem and you tested for it, then you're good, because then it falls into this region that we can understand. So we can kind of see this MGH tag in this saliency map. But if you didn't suspect the tag would be a problem and therefore didn't test for it, then subjects were not able to detect errors. So while explanations like these give some comfort that we can understand how machines reason, we also need to be skeptical of this comfort. It seems that in many situations, these explanations need to be used with great care to ensure that it isn't used to create trust when we really shouldn't trust the model. So far, Just quickly check the question. So far, I might have been a little green, but here's where this talk takes a turn. Let me talk about why vision offers unique opportunities, possibly the best modality to learn about the new machine concept. Why is that? Well, the machine's concept, this CM that I talked about, is it going to be something foreign to us? Just think about the Move 37 that AlphaGo made. It's going to be so complex that Go players are still talking about it. What about in science domain, something much more complicated and requires a lot of domain expert knowledge? It's going to be something that requires a lot of effort from human side. With that high complexity of the foreign concept, we need a vehicle or a modality that aid better comprehension. And humans are a lot better at grasping information in visual form, whether that's a collection of images or visualization of AlphaGo moves. The visual modality is likely to be the best, at least first, modality where we may discover new concepts that previously didn't exist in our representational space. Here are a few works that we've done over the years to learn a new concept in vision. So we leverage the fact that visual examples are powerful. This algorithm itself is pretty simple. We first divide this image into patches, what we call parts of image. And then we are using off-the-shelf superpixel methods. Then we decompose the embedding space using careful clustering or PCA. Now, each principal component or the cluster could be seen as a new machine's concept, but expressed in a way that we can understand and understand quickly. We do careful user studies to validate these discovered concepts, making sure that we are not fooling ourselves by comparing participants' performance on an intruder test. It's a type of odd one out test. You give them a few images and ask which one is an odd one of those of them. We compare performance of subjects to handcrafted, manually generated concepts. This is like the gold standard of actual concept. And only if our discovered concepts are as distinctive quantitatively as manually generated concepts, we can say that there is some meaningful consistency that we can understand in these new concepts. And that's what we show. So here are some examples of discovered concepts. For example, for a train class, it seems to be paying a lot of attention on the tiles on the platform rather than the train itself. For the dumbbell class, it's actually looking at the human in the picture rather than the dumbbells themselves. So this simple method already reveals so much about how machines thinking is different from how we would have guessed it. In the follow-up work, we also start to think about how complete these discovered concepts are, because perhaps and likely that not all concepts can be expressed using parts of images. And this method used here is also pretty simple, but harder, much harder to make it work. So we decompose the activation space into using concept vectors. Then we reconstruct images, embeddings, only using those concept vectors, and make sure while ensuring that reconstructed embeddings can exhibit the same behavior in the later layer, including the prediction. And so for each discovered concept, we also define Shapley values. It's a pretty simple extension of the Shapley value to estimate how much each contribute to the prediction. We also show that this completeness measure comes out to be equivalent to the top K PCA vectors, which is nice because then you get this nice theoretical properties for free. But maybe, and this question has always lingered us throughout all this work, is that we know that machines' concepts are going to be pretty wild. So maybe it can't even be expressed using our own images or patches of images. Maybe the best way is to let them draw it. So we investigate that in this recent paper. For example, in the dermatology domain, this is skin lesion, we can generate multiple different concepts. These are generated, or actually, these are just an illustration. Instead of showing heat maps, which we have plenty of, or do segmentation or retrieval, so that they can see and draw in ways that humans can understand. So this method is simple, again, to describe, also hard to make it work. We first list out all the desiderata. and corresponding mathematical definitions. So for example, stable generation means that when you generate explanations that something like the ones I just show you, they don't change very much as we resample the drawings. And here are some brief diagrams of how things work. I don't expect you to look at that and understand our method, but the high level idea is that we assume that we have a fixed classification model, but we attach a generated model. And this generative model actually uses derivative of this classification model to train. So it's using its own language, the derivatives and vectors, to transfer what it knows to something that we can understand, pictures. Here are some examples of our results compared to baselines. We test in some synthetic domain. This is synthetic domain. And before moving on to 3D shapes data, we also select D, but it's not shown here. So here are some, I'm hearing something. Nope. All right. Here are the baselines, EPE modification, and here are our methods. And as you can see, Dissect is able to find that you can change the bold color from purple to red to change classification, but also the color of the floor too. So some diverse and stable and realistic generation of these concepts that classification model use. So these are just a few initial directions to expand what we know. There's a long way to go, each of which has their own limitations. For example, the way that we validated new discovered concepts is using synthetic data set, as we did here, or in practice with domain experts. So then we thought, instead of developing general tools, what if we take a deeper dive into one special model to study how it sees the world? And that's what we did when we studied AlphaZero, a self-trained chess playing model from DeepMind, and in collaboration with a world chess champion. While this seemed like a non-visual domain first, note that the way that AlphaZero processes board positions are essentially vision data. Also later, we'll see that understanding new concepts using board positions mirrors this visual modality that we've been talking about. Self-trained means that it was trained by playing against itself. So it never ever saw how humans play chess. And that's interesting because if we can show it naturally learns to share some representational space with us, that gives us hope to expand what we know. And this AlphaZero is not just any self-trained chess playing machine. It plays it very, very well. It beats the Stockfish engine, which is arguably the best chess engine out there. Some might argue that there will be no human, including chess champions, who could beat Stockfish. And this AlphaZero beats a Stockfish only after 4 hours of training from scratch. And we're also fortunate to have Vlad, a former world chess champion, and also co-author of this paper, who has better chance of talking to this model than any of us and provide some qualitative insight. So the first question is, do human chess concepts exist in AlphaZero, or does it just learn to play completely different way? We use very simple linear props to detect concepts. We have concept labels from Stockfish. Then for each layer, we train a linear classifier to distinguish concepts from others and use the accuracy of the classifier as a proxy for whether the concept or something correlated with the concept, to be exact, exists in each layer throughout the course of in each layer or throughout the course of training. And it turns out that it does, but what concept is learned when and where varies. For example, material imbalance, briefly put, it's how many pieces you have left, how many pieces I have left, is learned and then forgotten as AlphaZero gets better at playing. And others, like in check, which is pretty critical for winning the game, stays learned throughout. Now, what's interesting is that one can argue that material imbalance is something that novice chess player might use to play at first, but experts know that an imbalance isn't enough to win the game. And it seems like AlphaZero is going through that similar phase too. Thanks to data from ChessBase, we can also compare the evolution of human chess playing versus AlphaZero. So this graph on the left is the proportion of different opening moves. This is like the first move you make when you play chess, and how they evolve over pretty much the entire human recorded history of chess since 1400. And on the right, I'm showing you AlphaZero's opening move as a function of the training steps, and they look very different. It's particularly interesting how AlphaZero has more diverse set of opening moves than humans. In other words, AlphaZero may have a different ways to play that leads to wins. So for example, if human trying to play against AlphaZero, they would have to cover potentially a lot more strategies and master because it masters just different ways to open the game, and that leads to winning. And we try this train AlphaZero with different seating and same architecture, same everything, and it ends up being very similar distribution. So it's also interesting that there seems to be a point at which things click for AlphaZero, and it also chooses the style of play. It's like right here around 64,000. And this explosion of skills, which we call, aligns with Vlad's qualitative assessment. We gave him a lot of games, 100 games each at each training point. And this is something that also Vlad observed without having seen our quantitative observation of the value function or the loss function as we train this AlphaZero. So finally, we take a first step towards expanding what we know. This is a small step. We don't do anything fancy. Because validating a new chess concept is likely to require many more than one chess champion. So we need to recruit more chess champions perhaps, so that's going to take time. But in the meanwhile, we explore simple technique, non-negative factorization to find decomposed activation space and visualize that activation space with a strong assumption that spatial relevance is maintained. So layer, we call it blocks, but layer 20, AlphaZero's architecture is laid out such that all the dimensions in all layers are identical to chessboard, so it doesn't grow or it gets reduced. And under that, we have this assumption. We thought this assumption is reasonable, so we visualized it accordingly. And many concepts that we discovered remain mystery. So here are two concepts that we think we might have an idea of. For example, this block 1, this is first layer, factor 26. You can kind of see maybe it's representing diagonal moves for the player. In some later block, perhaps this vector represents potentially good move. We don't know. But here's a tool that you can visit and explore AlphaZero's representation in place. Especially if you play chess, you can go to this link and view discover concepts, and there's a form you can submit if you do discover something and want to share it with us. There's you can form that you can fill out. We are actively working on a follow-up project, and we rely even more heavily on visual modalities in discovering new chess concepts. So to conclude, vision domain holds huge, if not the biggest potential in bridging the representational gap between humans and machines. And I personally, learning a new machine concepts and translating it to what we can understand in complex domains like chess or science is where I believe the next machine learning breakthrough is going to come from. But the great power comes great responsibility. Let's stay extra vigilant to ensure that what we do is meaningful. Alternatively, ultimately, to ensure that this language that we're developing can shape our working relationships with machines and AI. With that, I would be thrilled to accept any questions you might have. Thank you.
Thank you, Bin. So do we have any questions from the audience here in person? Dipti, do you have any questions on your side on Zoom?
Yes, there is one from Andang. During my study, I found that in many situations, the concepts model learned may be a mixture of human understandable concepts. If that is true, I wonder, will the vectors CM and CH that you mentioned in the beginning of the talk, would they be interfered by the mixture of concepts? Or is there a better way to disentangle those concepts?
Yeah, these are interesting questions. So there are lots of parts in this question. So one is doing this for concepts that we know or concepts that are new to us. So let's talk about concepts that we know first. So for concepts we know, it seems reasonable to have these bases, like maybe we want most primitive concepts as the beginning and maybe combine them together to express more complex concepts, like what you're saying, mixture of concepts. The challenge there's lots of challenges. The challenge there is that there's a huge field in psychology of concept learning about humans, how humans define concepts, what humans use, how human uses concepts. So for example, if I ask Dipti that, oh, what are you sitting on? Then Dipti might say, what are you sitting on?
A chair.
Right, you said chair. So you didn't say, oh, chair that rotates with wheels, a chair that has or 4 legs, or blue chair or black chair. You didn't say that, you said chair. So there's studies that consist of these sort of experiments that show humans apparently latch on a certain level of concepts that to communicate this basic information. And it's nothing more than or less than that level. Now, there's a lot of controversial thoughts along this line, and all that is to say, TLDR, is that even defining the most primitive set of concepts is really hard. It's an open research question. So there's a challenge. For using those concepts as a machine to learn about new machines concepts, I actually think that would become essential. So again, these machines concepts is going to be foreign to us. It's going to be weird. It's going to take a lot of time and effort to understand it. So then one way to empower that process is to learn some primitive concepts and put a lot of effort into understanding those, then start mixing them up in intelligent ways to understand even more complex concepts. And I think we use this compositional ability for a lot of things, like when we're coding, we write a lot of functions, and at the end of the day, you might have 10,000 lines of code, but pieces you understand, and that enables you to debug and work with code. And similar idea, like this language with machines, will come true, is what I believe. So I often talk about how I imagine, when my son goes to school, maybe he will learn this language to talk to machines at school, just like we learn math or English in my case from Korea, because that's useful and it's essential to daily lives.
Okay, we have one more question in person here, and then we move on to the next invited talk.
Yeah, thank you for the amazing talk. I just kind of like a high level question. I wanted to get your thoughts on whether, because there's various types of explanations that are like continuous, like a saliency map, or discrete, a language. And I wanted to get your thoughts on where you think the field is kind of going. Like, should interpretations for humans to understand them go more this discrete route and maybe be language, or are there scenarios that we really want to have these more continuous representations of interpretability? And like, just I wanted to get your thoughts on that continuum.
Interesting question. And my answer may not be as satisfactory as you hoped. I think it depends. I believe, and I still think I believe that explanation should align with the way we see the world. So for example, vision, we don't see the world digitally. We see analog world. Things are mushed together. We don't see pixels. So in that domain, it feels like it would be more natural for explanations to align with the way we understand the world, right? So if either continuous or per object, because for us, the world consists of objects, backgrounds, and things that are together rather than all equal parts of this pixel is different from that pixel. It's just me here, and then that's the chair, and that's how we see the world. And that's what I generally believe in. Concept-based explanations would better align, especially in that domain. Moving to like medical domain, where doctors are really, really trained to think in the terms, glands fusing together means something very medically significant, that this pixel getting more important or bluish than this other pixel. So it really needs to align there. Language is a funny thing. I think language always tricks me off. Like the challenge in language is that we as a human don't really have a greatest clarity on meanings of a language. We use same words for different culture uses different words in different ways. Humor are very different in United States than Korea. Like sarcasm doesn't really exist in Korean language. It's kind of weird, but you know, Americans understand sarcasm, and I fully enjoy it now. So given that lack of sort of ground truth, it's difficult to see what kind of explanation or where we align better as a human. Is it continuous or is it kind of discrete, as the surface level representation would reveal? Like it's words, they're sentences, they're put together. I don't think it's that simple. It's a lot more complicated than that language is. And the actual linguist would be able to answer this question a lot better than I can. But again, I think in that domain, it should align better with how humans reason.
Amazing. Thank you.
Okay, let's thank the speaker once more.
Thanks for having me.
Thank you. Thanks, Bean. It's been great.
Thank you. It was a great talk. Okay.